Hello and welcome to the course Design Borefields with Confidence. This is the fourth chapter of the second part. It's the last chapter, and finally we will be taking a look at making our first geothermal simulation in GHEtool Cloud. Now, the last chapters we talked about temperature profiles, what we can see on them. We talked about the effective borehole tunnel resistance, which was the relationship between the borehole wall temperature and our fluid temperatures. And we also talked about the G functions, the ground response functions, to see how the temperatures evolve over the seasons and over the years. And now let's bring everything into practice and simulate our first geothermal project in this chapter. And we're also going to do that with some basic and traditional assumptions. Now, as said in GHEtool, you can go quite far with quite advanced methods. Now we're going to toggle off some options in order to make sure that we start with the basics, and over the next couple of parts we're also going to increase the complexity and toggle these options back on to show you also the difference in accuracy and in insights when you compare basic traditional borefield design with the more advanced methods that are available in GHEtool, but more on that later. So for the example case today, we're going to look at an office building in the city of Ghent in Belgium. It does not matter where it's located actually, but let's look at the project in Ghent. And the goal is that we size a borefield for a high cooling demand. Now, later this course, you will see that I would say sizing for cooling gives you more interesting insights in everything than when you just sign for heating. So it will be a project with a very high cooling demand. And we will also learn about the influence of the thermal gradients. And so as we said, the ground becomes warmer when we go deeper. So what's the effect on this when we're sizing our system? We will talk about the difference between monopropylene glycol and just using water for a geothermal system, as well as single MW. So we will not cover everything, but these are some basics that will give you some insights in, basically everything we talked about so far, but now for a particular project. So some general input parameters, let's use 40 years as a simulation period and our default 2 and 17 degrees as temperature limits. For our ground, we know that our average homogeneous ground thermal conductivity is 1.6 watt per meter Kelvin if we drill to 150 meters. And if we drill to 100 meters, we know it's 1.7 watt per meter Kelvin. So we're not yet going to use ground layers here. We're working with two distinct values. We have a certain volumetric heat capacity and the location is Belgium, Ghent. Our borefield, I will, when I show you my results or answers, always work with a rectangular borefield with an equal spacing in length and width of 6 meters. We will use a buried depth of 0.7 meters. And we will start off with initial design of 15 by 14 boreholes of 150 meters borehole depth. So as you can see, it's already quite big, a big project. For the borehole resistance, we will use a traditional DN32W probe. The borehole spacing and grout, etc. are default values. And for our fluid, we will use 25 volume percent of monopropylene glycol and 35 liters per second of flow rate through our entire borefield, which we will assume to be constant in time. And then lastly, for our thermal demand, it's a building demand. It's in heating and cooling demand. The heating is 306 kilowatts as a peak power with almost 400 megawatt hours per year of heating demand, certain efficiency of the heat pump. And for cooling, it's 336 kilowatts with a slightly lower energy demand of around 270 megawatt hours per year. It will be passive cooling, so our SEER, our seasonal energy efficiency ratio, is around 20. Now, these were the inputs. Let's go over to GHEtool to actually see how you can simulate this project in the software and also see how you can vary certain parameters so we end up with some interesting results and sensitivity analysis. So here we are on our website, which you probably already know if you're following along with this course. You can find the course here. We have our knowledge base articles over on our website. But now let's go ahead and click on the Cloud button. Now, if you have not registered for GHEtool or you don't have an account yet, you can register for a trial period of 14 days. You can also schedule a demo call with me to discuss about GHEtool one-on-one or what value it might have for your company. But I already have an account, so let's go ahead and log in. So here we are on our project dashboard. Some more administration will be over on the admin dashboard, like company and licenses and layout of your custom report and so forth. And to the left, you will find all your projects. Now, let us go ahead and create a new project. As you can see, I already did some simulations to prepare for this chapter, but let's call it course 2.4, my first simulation. Let's go ahead and create this. And I'm not going to explain everything about GHEtool in this video over the next chapters and the whole duration of the course. We will explore every functionality. We will keep it today for the basics, what is really needed for this simulation. What is important to note is that GHEtool is scenario based, which means that if you do a certain simulation and you want to change a couple of parameters, we're going to duplicate the scenario so we can easily compare different design options, design choices next to each other. Also, if you are not speaking English, you can change your project language over on our project dashboard, as well as the report language, which is also available in French. And more languages will be added later, by the way, if you want to make a report out of your simulation. Now, let's go over the information we talked about in the slides. We're going to calculate our temperature profile. So today we're going to do everything manually, not going to use automated sizing, because we want to really feel how the borefield sizing behaves. So we're going to work with 2 and 17 degrees and 40 years as a simulation period. And here we have an important setting. We're going to set the temperature dependent fluid properties to no. Next part, we will set it to yes, because it's way more insightful, way more detailed, way more accurate as well. But for now, to keep everything simple, let's set it to no, because that's basically the traditional way we've been designing borefields over the last decades before the introduction of more advanced methods in GHEtool. For our ground properties, we will start with the borefield of 150 meters deep, and that was 1.6 watt per meter Kelvin. And for the location, we used Bel Ghent. This is, by the way, a data set of the whole of Europe. There are quite a couple of locations, but perhaps your local government or geological department has some more detailed or more accurate information. So this is just our database. For the borefield, it was using 15 by 14 boreholes of 150 meters borehole depth with a buried depth of 0.7 volts. Now, I just want to say a couple of things about terminology here. GHEtool has this concept of the buried depth, which is basically the depth at which your horizontal connections are installed. So if you have the ground surface, typically almost a meter below is your horizontal network, and then your borehole starts. So if we drill 150 meters deep and we connect everything at 0.7 meters below surface, our borehole is actually 149.3 meters long. So that's a little bit the idea here. 15 by 14 and 6 by 6. So we have here a certain footprint and a certain total borehole length. So it's indeed quite a big project. A borehole resistance. We have here all regular probes. You can add custom, and we have some commercial ones as well, which we will also cover later in this course. All these values were the default values, 25% of monopropylene glycol. Also, this you can enter if you want explicitly, but please just use the database. It's way faster and more accurate, especially later on. And for the flow rate, we're going to work with a constant flow rate for the entire bore field, which was 35 liters per second. Now, just a couple of things here. Typically, our most common is to use a flow rate per borehole. Now, that also works, but the problem is that if you change the number of boreholes, you also need to update the flow rate for each borehole. So therefore, we're going to, it's a good practice, let's say, to work with a flow rate for the entire bore field, so that when you change the number of boreholes later, your flow rate is not messed up. So that's why we're working now with 35 liters per second for the entire bore field. And later on in this course, we will talk about how you can actually calculate this, but also how GHEtool can calculate it for you. But that's for later. Now, let's end with our thermal demand. So we work with a building demand and not a geothermal demand. And let's use an efficiency of 4.5 for heating. The peak duration, let's keep it for what it is. We will come back to that next part. Let's work with relative loads. So then we can use a certain distribution and we just have to enter our peak powers and yearly demand. So it was 306 for heating, 336 for cooling, and the yearly demand, let's put it in megawatt hours to keep it easily readable, was 398, and here it was 269 megawatt hours. So let us go ahead and simulate that. And in just a couple of seconds, we will have our results. So here we see our minimum and our maximum temperature in both peak and base load. Now, as we said before, some countries also have legislation related to base load temperatures, which is visible here. We have our average undisturbed ground temperature of 13.27 degrees Celsius. We have a certain effective borehole thermal resistance and a certain Reynolds number. And here you can clearly see our temperature profile. So for 40 years, quite a lot of seasonal variety, but we see some imbalance. So in our first years, we are at 17.17, and we go to just below 17, I believe. 16.8. So it's quite a small imbalance. You almost don't see anything. And we are slightly above our 17 degrees Celsius limit. Now, the reason I want to start with this design is to discuss a little bit the flexibility on these maximum temperatures and minimum as well. So strictly speaking, you could say, well, this is not designed, it's not within limits, etc. But of course, you've seen what a gigantic project it is at 210 boreholes. And we're doing this with just yearly values. So the uncertainty on the inputs is quite big, I think. And the thing is, just look at this at the moment as a sort of feasibility study. So if you're designing such a big project and you're working with such a big uncertainty on the loads, chances are there is already quite a lot of backup or oversizing in your energy, in your peak powers. And if that's the case, then your 17 degrees is not that strict. It's my opinion. But of course, if you know that your peak powers are on the short or on the small side, then it's more important to keep you really within certain limits you set yourself. So it's all a little bit about where do you take a certain safety factor into account. In our case, there's quite a lot of safety on our load. So 17.19, I would say, is okay, especially since we have this imbalance and year after year, our temperature will be going down. Now, that was our initial situation. Let us go ahead, duplicate the scenario, and see what we can do if we, for example, say we drill to only 100 meters. So imagine there is a difficult ground layer at, for example, 110 meters, and we say, okay, let's stick to 100 meters. So we're going to go to the borefield tab, and we change to 100 meters. Now, if we now simulate this again, yeah, we will find out that our borefield is too small because we cut away 30%. But strangely, perhaps, you see indeed our temperatures are now not 17.19 maximum, minimum is still fine, but 17.5, which is, yeah, in my opinion, already a little bit too far above 17 in this case. But I would have expected way more. We decreased the total borehole length by a third, and we only increased by a couple of tenths of a degree. And the reason for that is that our average undisturbed ground temperature was previously 13.3, basically. Now it's only 12. So by drilling less deep, due to the gradient, our undisturbed ground temperature is actually colder, shifting all the lines lower. So that's why we don't have this, or an unexpectedly low maximum fluid temperature, let's say. But what you can also see is that our range between the maximum and the minimum limits, visually, it's significantly larger. And that is because if you recall our short-term effects, and we have our borehole resistance, which is, okay, it changes a little bit, but conceptually, it's not only the borehole resistance that's of importance, but also the total borehole length. And we decreased the borehole length by a factor, of 1/3. That also means that our specific heat exchange per meter borehole increased significantly. And this makes why the temperatures are now, they now show as a bigger range between maximum and fluid. So the sinusoidal amplitude is bigger, if you want. So this was if we change the depth. So let us go ahead and see how many boreholes we should add. Let's add 15 boreholes here. And just to play around a little bit together with you. So now we're at 17.80, and yeah, we're in the same range. So we only need 15 boreholes less, but we could decrease the depth by a factor of a third. So our total borehole length was 31 kilometers, and now we're at 22 kilometers. So that's already quite a lot of difference. But one thing we forgot, not accidentally, I should mention, is that we said, well, if we drill to only 100 meters, also our ground thermal conductivity was a little bit better. So it's now 1.7. And this illustrates that if you work with this homogeneous data, it's really important to keep track of your different depths, because if you change your depth, chances are your conductivity should change as well. Because if we do that, you can see that our maximum fluid temperature is now below 17 degrees when you compare it to the previous case. So this is really important and significant that by just changing 0.6 to 0.7, we are now below our threshold. So one could argue that perhaps we can decrease the number of boreholes a little bit. Let us perhaps just try that. Make it 14 again. I doubt it will be within limits, but just to see. Yeah, 17.22. Let's call it okay. And then we see that in this case, going from 150 meters to 100, due to the better thermal conductivity of the ground, we get almost the same results, but with a third less borehole meters, which is actually quite interesting, I believe. Now, let's do something about this borehole resistance, shall we? Because we have a laminar flow rate, not too bad at borehole resistance at 0.15. We can do better. We just have quite a lot of boreholes, so the flow rate in each borehole is not that good. But what we see is that our minimum fluid temperature during peak is almost it's 7.5, and we are working with monopropylene glycol of 25%. So we have freezing protection to -11, which we actually don't need. So let's go ahead and say, okay, can we work with water instead? And when we do that, yeah, you can already see it spoiled here. Our Reynolds number increased significantly because water has way lower viscosity, as we will discuss next part. So also our effective boil thermal resistance is now way better because, yeah, our convective heat transfer is now way more efficient. So if we simulate this, so all the rest is the same, we just say, okay, we don't need this antifreeze. We see that our temperatures, our maximum temperatures, are even lower because our resistance, our effective borehole thermal resistance, is now better. So let us go ahead and duplicate this to see if we can, for example, again take away some of the boreholes. Let's see if we can take again 15 boreholes away from our simulation. And yes, we can, because there are now two effects playing. Okay, we had some spaces. So in scenario 4 we were at 16.76. So if we decrease the number of boreholes, our specific heat ejection in this case would be bigger because our total borehole length is now smaller. But what also is interesting is that here we are in the transient range at 2440. We know that turbulence starts at 2300, so we're absolutely not yet turbulent. But by decreasing the number of boreholes, our Reynolds number increases because, yeah, our flow, it is what it is, and it has to be divided amongst the different boreholes. So by reducing the number of boreholes, we would again expect our temperatures to rise significantly. But now, because our effective borehole thermal resistance also decreased by almost 10%, this effect is again counterbalanced. So it is already clear to you, I presume, that the classical rule of 3 is not applicable in borefield design anywhere. It's just too, I would say, complicated, but I'm going to say interesting, that all these aspects they work together. They counteract also each other. So it's really something that needs quite a lot of nights good sleep to really understand how the system is going to work. So let us also, to make it sure, we're now still working with 2 degrees as a minimum, which is not that accurate. If you work with water, typically you want 6 degrees as an average fluid temperature, so regime 4 to 8, to really make sure nothing is wrong there. And what you can see here, if we do that, just for your information, that the Reynolds number again changed. Now, why is that? It is because our minimum average fluid temperature, and that's here, is actually the reference temperature to calculate the viscosity of the fluid and the resistance, etc. So by setting it to 6, we actually increase the temperature, basically increasing the Reynolds number. But we will come back to that in one of the next chapters, so no worries about that. Now this was for a W tube. Let us see what the result would be if we go for a single one, because we also talked about that in the last chapters. So what we then do is we say, okay, number of U-tubes 1, done. And what you can see already immediately, let's just go back. We were at rather transient at 3000 Reynolds. It's already good turbulent. I would say starting to become good turbulent. Quite a good borehole resistance as well. If we now make it 1, we are absolutely turbulent, almost 6000. but our borehole resistance is a little bit bigger. So let's calculate that. And the reason for that is, if both are turbulent, in this case our convective heat transfer will be even better due to the high Reynolds number, but we have now one probe instead of two. So the heat transfer area is only half what it was in scenario 5 with the W probe. And that now counteracts our effective borehole resistance. So here we are again having a slightly higher temperature than in scenario 5. Now, what we could do is, instead of saying, okay, we're now working with a single DN32, we could, for example, say, let's use a single DN40. Because we will be turbulent, the flow rate is high enough per borehole, but if we have a DN40 instead of a DN32, our surface area is again bigger. And the advantage of a single DN40 is that it's easier to install. It's probably also a little bit cheaper. So let us simulate that scenario and see how that one looks. So here we can see indeed a slightly smaller resistance and a temperature really close to our threshold of 17 degrees. So scenario 5 was with a W, 16.9 degrees Celsius, below our threshold. Actually, we could potentially decrease the number of boreholes here somewhat further. We have scenario 6, where we move to a single U. Here the temperatures are higher because the borehole resistance is a little bit bigger. And then we have scenario 7 with the DN40, still slightly above our maximum limit, but actually I would say this is a rather good design, and we are still above our 6 degrees average, even quite a lot above it. So it would be safe to do this system with water. So I hope you found this already interesting. I would highly suggest that you try playing around with GHEtool yourself, because the 7 scenarios I did are just to show you some interesting aspects, single, double, water, monopropylene glycol, temperature gradient, and so forth. But to really understand all the different physical aspects, it's important that you get this confidence yourself. So knowing is one thing, but seeing it and understanding it is another. And we will do quite a lot of sensitivity analysis throughout the rest of this course, and it will only be more and more advanced from now on. So if you want to keep track of everything, just give it a go yourself. And I'm looking forward to seeing you in part 3 of this course.